Okay, so today's lesson is going to be on single replacement reactions, and we are going to be on our single replacement section of our reference tables. We have two main types of single replacement reactions. We can have a metal that replaces another metal, or we can have a non-metal that replaces a non-metal. Now, when we're looking at our reference tables, in order to determine if the reaction is going to happen, we're going to use our activity series. So we have our activity series for the metals, and we have our activity series for the nonmetals, which these are the halogens, fluorine, chlorine, bromine, and iodine. For our activity series, in order to determine if a reaction is going to take place, you are going to look at the order. Top can replace bottom. So lithium could replace rubidium, potassium, barium, strontium, etc. But sodium would not be able to replace lithium. So let's take a look at some of these examples and see if we can't try and make more sense of our activity series. All right, so what we have here is magnesium and zinc nitrate. Magnesium takes zinc and kicks it out. So zinc is by itself and magnesium combines with the nitrate. So magnesium is kicking zinc out all by itself. Now let's see if this is actually going to happen, and that's where we come back to our activity series. And on our activity series, here's magnesium, and then we're going to find zinc is right here. Magnesium is above zinc, so this reaction will work. Notice our arrows over here tell us some things, okay? So lithium through sodium can replace hydrogen from cold water. If we go through cadmium, we can replace hydrogen from steam. That would be gaseous water. All right, here we've got our line through our acids and then reacts with oxygen to form oxides. So we have some things as well, some additional rules with the lines. But magnesium will replace zinc, which is our most basic type, just looking at the activity series. So what I'm going to have to do first, I'm going to have to balance my equation. And I see that it is in fact balanced. So now I'm going to write a complete ionic equation. All right, and this is where I'm going to take all of my aqueous. Now remember, aqueous means dissolved in water. So it is in the ion form. Magnesium is a solid. Solids, we are saying, are not dissolving in water, so we're going to write them as is. Same thing with the liquid or gas. We're only going to break apart the aqueous components for our complete ionic equation, never the solid, liquid, or gas. So zinc and 2 nitrates is going to yield magnesium ion because it's an aqueous, 2 nitrate ions, and my solid zinc. Now, we are going to go through here and we are going to pull out the spectator ion. What is a spectator ion? A spectator ion is an ion that is present in the solution, but it's not involved in the actual reaction. So if you go to a football game and you're up in the stand and you're cheering on our team on a Friday night home game, does our team score a touchdown because you were in the stands cheering? And the answer to that is no. You were not involved in that play on the field, which led to a touchdown. You just happened to be there cheering on the team. But the touchdown was not because you were there, it was because the player on the field actually scored that touchdown. So that's what a spectator ion is. It's present, but it's not involved. So a single replacement reaction, let's look here. On this equation, I have a solid magnesium as a reactant, and I have solid zinc as a product. So I have two things involved in the reaction. Nitrate is not part of the solid on either side of the equation. So nitrate gets marked out. To create solid zinc, I have to have a zinc ion. If a magnesium solid, it's going to create an ion because of the law of conservation of mass. Mass is not created or destroyed, it simply rearranges. So I cannot form zinc if there is not some sort of zinc ion present. So when we want to write our net ionic equation, that's going to be everything that we did not cross out. So the magnesium solid, the zinc ion, will form a magnesium ion and solid zinc. So here's our overall net ionic equation. All right, let's check out the next one. Lead and hydrochloric acid. So when I look at my activity series, I'm going to find lead, and here's lead, and it is within the line replaces hydrogen from an acid. This line goes all the way down, all right? Lead can replace hydrogen from an acid, so this reaction will work. So what are we going to do? Let's start with our complete ionic equation. Any solid, liquid, or gas we leave as is. We only break the aqueous apart. And I need to balance this equation, which I forgot. So let's put a 2 in front. So I have 2 hydrogen ions, 2 chloride ions. Lead 2 chloride is aqueous, so my lead, and that's a 2 plus. My chloride, I have 2 of them. And then my hydrogen gas. All right, so here we have a gas, the formation of a gas, and that's okay. We could form a solid, a liquid, or a gas. So what do I notice? I have solid lead, and I have gaseous hydrogen. So chlorine is not part of the lead or the hydrogen, so I mark that out. And I simply rewrite everything that is remaining. All right, and there is my net ionic equation. Solid lead becomes aqueous lead, and aqueous hydrogen becomes hydrogen gas. Law of conservation of mass here. What goes in, comes out, is simply rearranged. Magnesium plus silver nitrate. So when I look at my activity series, magnesium is higher than silver, so this reaction will work. So what are my products? Magnesium is going to kick silver out by itself. So silver is going to be all by itself, and now anytime we have a metal by itself, it will be a solid. So you know the state of matter. If you have a metal by itself, it is a solid. So magnesium now combines with my magnesium nitrate, and then we simply have to balance our chemical equation. And then we're going to move to our ionic equations. Here's my solid. I'm going to break apart my aqueous into their ions, because that's what aqueous means, ions. Dissolved in water to form ions. My silver is a solid, and this is going to be aqueous. All right, we know. Here we got magnesium ions. and 2 nitrate ions. So what do we have? We have solid magnesium and solid silver. So nitrate is not involved in the formation of either one of those solids. So we're going to mark that out and simply rewrite everything that we are left with. And there is our net ionic equation. So in chemistry, we want to make sure we're writing net ionic equations because that is what we care about. What is actually involved in the reaction? Chemistry is the study of reaction, so we want to know about what's involved within that reaction. All right, let's check out number 4. Copper replaces iron. So coming back to our activity series, and here is iron, and copper is below it. Copper is below iron, so copper cannot kick iron out. If it is below, it cannot work. This would be a no reaction. So we don't have to predict products, balance, write a net ionic, nothing, the reaction doesn't occur. So we're just going to write no reaction and move on. All right, aluminum bromide plus chlorine. Now, I have a bromide and chlorine. Those are both halogens. So I've got to come up here to this activity series. And what do I notice here? I notice chlorine is higher than bromine. Because chlorine is above bromine, this reaction will work. Chlorine is going to kick bromine out. Bromine is now all by itself. Bromine is diatomic. Remember our 7 diatomic elements. All right, let's just do a quick review of our 7 diatomic elements. I like to remember that through Hunkelbrith. And these are our 7 elements that appear when by themselves, not combined with anything else, not in a compound, simply by themselves. They are diatomic, di meaning 2, atomic atoms. So H2, O2, N2, Cl2, Br2, I2, and F2. Now, some important to remember. Most of these diatomic elements are a gas at room temperature. Iodine is going to be a solid at room temperature, and bromine is a liquid. So that's important to know here. Bromine is a liquid, iodine is a solid. The remaining are all gases. And now this is a concept that we're going to explore in AP Chemistry and Honors Chemistry too, if you choose to take that next year. We'll go into a little bit more about trying to figure out why some of these states of matter are different. Why is iodine a solid and bromine is a liquid? For the purposes of our class, just knowing that is appropriate. All right, so this is a liquid, and we're forming aluminum chloride. All right, and so then I simply have to balance my equation here. So that's a 3. And that should balance. Yes. Okay. So again, we're going to break apart all of our aqueous. I have 2 aluminum ions. 3 times 2 is 6 bromide ions. I have 3 chlorine gases. 2 times 3 is 6. I have 6 chlorine gases. 2 times 3 is 6 liquid bromines. Oh, you know what? Let me start over on this one. I'm sorry. I completely just confused you, did I not? Let me start over. 2, I just pulled an honors chemistry move here. All right, so my aluminum bromides here are aqueous. So I'm going to break them apart into their ions. So let me just start over here. I have 2 aluminum ions. 2 times 3 is 6 bromides. Now, I was originally correct here. I don't want to make this into its ion form. This is a gas. Remember, you cannot break apart a gas. So I totally just pulled an honors chemistry move and made the same mistake that you guys often make. This is a gas, so you need to leave it as is. It's 3 chlorines. There are 6 bromines total, but they are in their diatomic form as a liquid, so I'm going to leave them as is as well. And then I'm going to break apart this into its aqueous components, 2 aluminum ions plus 3 times 2 is 6 chloride ions. So what do I have as my equation? I have gaseous chlorine and liquid bromine. Aluminum is not part of the formation of the gaseous chlorine or the liquid bromine, so I'm going to mark that out. And my net ionic equation is going to be everything left over. 6 bromine ions plus 3 chlorine gases will yield 3 liquid bromines and 6 aqueous chloride ions. So there's my net ionic equation. All right, let's do our final example. All right, our final example here. And that is sodium bromide is going to combine with iodine. So we're going to notice here bromine and iodine are halogens. So we're going to look at our halogen activity series. Iodine is lower than bromine. Iodine is lower, so iodine cannot replace. This is a no reaction, so we don't need to predict products, balance, or anything like that because the reaction does not actually happen.